All right, we're going to continue doing AP review. This is 2009 Form B, AB and BC Free Response 2. All right, so this is a calculator question, so we will be using our calculator for some stuff and some things. All right, cool. A storm washed away sand from a beach, causing the edge of the water to get closer to a nearby road. The rate at which the distance between the road and the edge of the water is changing during the storm is modeled by f of t equals the square root of t plus cosine t minus 3. Notice that that's the rate at which the distance is changing, right? This is going to be one of those rate in, rate out problems, whether it's volume in, volume out, sand in, sand out, line of people getting on a ride versus lines of people getting off a ride. Like, it's going to be rate in, rate out. So this is the rate that the sand is disappearing, right? So that's a rate the sand is going away. It depends on how you're measuring this. It's a rate the water is, like, the distance is decreasing, but anyway. The edge of the water was 35 meters away from the road when the storm began, and the storm lasted for 5 hours. They give us the derivative of f as f prime equals this lovely 1 over 2 root t minus sine t, which is not a difficult derivative to find, but they were doing you a solid by saying you don't have to. All right, so part A, what was the distance between the road and the edge of the water at the end of the storm? Okay, so this is that first fundamental theorem of calculus question that we've seen a lot, right? You're going to use your calculator to do the number crunching, but you have to be able to set this stuff up. So this is the rate that the distance is changing, right? So if I want, so in my brain, right? So my brain, right? In my brain, I think of the fact that I'm going to, in my brain, think that the distance is, let's say, d of t, right? So if I say d of t is the actual distance, then f of t is actually the same as d prime of t. This is d prime. I'm not saying you should change that notation, but it helps to realize, oh, hey, this is the thing they're asking about. This is the derivative of that thing. This is the rate. So if I were to integrate from 0 to 5 of f of t dt, remember, in my brain, I'm thinking, oh, this is the derivative of the distance with respect to time. I'm going to get the distance, right? So essentially, I'm going to get the distance at t equals 5, right? So this quantity minus the distance at t equals 0, because that's how the first fundamental theorem of calculus works, right? If I'm integrating d prime, I'm going to get, again, using my notation, d of 5 minus d of 0, right? And this is the thing I want. So I know d of 0. I'm told that there are 35 meters between the road and the water at the start of the problem. So essentially, this is going to get added over. And the distance, so the distance at t equals 5 is going to be, this 35 is going to get added over. So 35 plus this integral, which is something I can make my calculator do, right? So this is what the AP needs to see from you, and then they just want you to type and get your answer, right? So it's 26.494 or 5, and it's in meters, right? So this is what an AP needs to see from you, right? How you get there is up to you, right? In my brain, I always say, oh, wait, this is a rate, distance is changing. Let me assign a function for distance, and then I will think this in my head so that I don't get confused about what's happening. So again, you're probably going to put this in as y1, and it's probably going to be in terms of x. So you're going to put root x plus cosine of x minus 3, right? You're going to do math 9, which is function integrate of y1 with respect to x from 0 to 5, and you're going to add a 35 to that, and that's how we get this number right here, right? Make sure that you include units because there are units in this problem. All right, so that's part A. Part B, using correct units, interpret the value of f prime of 4 equals 1.007. So in terms of the distance between the road and the edge of the water. Okay, so they're giving us a value. They don't want you to do any calculation. They just want you to understand the relationship. So what I want to make clear, right? So if this is, okay, so again, in my brain, I say, oh, distance is like d of t. That makes this d prime of t, right? Which is the rate or sort of velocity, right? For lack of a better way to think of it, that this is changing, right? Velocity. That makes this d double prime of t, meaning that this is the acceleration with which this thing is changing. So when we look at part B, if f prime of 4 equals 1.007, right? That means that what's happening is 4 hours after the storm begins, right? So 4 hours after the storm begins, the rate of change of the distance, so the rate of change of the distance between the road and the edge of the water is increasing, because this, okay, so this, right, so f of t is increasing, right, because f prime of t is positive, which means f of t is increasing. So the rate at which the distance is changing is increasing, right? So that's what we want. So essentially 4 hours after the storm began, the rate at which the distance is changing is increasing. That's essentially what they want. And they want is increasing, sorry, at 1.007. It was measured in meters and hours, so meters per hour squared, right? Because it's essentially an acceleration, right? If you think about distance measured in meters, f of t was actually like our d prime, which is sort of like a velocity, meaning meters per hour, and f prime of t, which is the same as d double prime, should be essentially the acceleration, right? Okay, part C. At what time during the 5 hours of the storm was the distance between the road and the edge of the water decreasing the most rapidly, right? So when essentially what you want is the max of f of t, right? So when let me give myself some space, right? So what they ask you is in the window from 0 to 5, right? So part C, right? In the window from 0 to 5, when is the, just double checking that I'm wording this right. Well, at what time was the distance between the road and the edge of the water decreasing the most rapidly, right? So when is distance decreasing most rapidly, right? So the trick is, if you want decreasing most rapidly, that's asking, so that asks when is f of t its most negative, right? That's asking when is f of t its most negative, right? So essentially that's asking for a min, right? What we're being asked to do is we're asking to find extrema for f of t, right? So if you want f of t extrema, right? So when you want f of t extrema, you use f prime of t, right? So we want critical points for f of t. That means we use f prime of t. So the possible critical points come in 3 basic varieties. Option number 1, f prime of t equals 0. Well, we can use our calculator to find that, right? I can put y2 in my calculator as a 1 over, in parentheses, 2 root x, close everything, minus sine of x, right? And I can calculate when those values are 0, right? The second kind of critical point is when f prime of t does not exist, right? And f prime of t does not exist at 0, right? Because if you look, you can't actually plug a 0 in there, right? So it doesn't exist at 0, right? And that's about it. That's really the only time you'd have to worry about. So it doesn't exist at 0. So f prime of t doesn't exist when t equals 0, but that was already a critical point, because the third kind of critical point are the endpoints, and that's when t is 0 and 5. So essentially, I'm going to use my calculator to find these critical points, right? I'm going to second calc 0. And when I second calc 0, I'm going to get that there are 2 spots where this entire monstrosity equals 0. They are at t is approximately 0.66187 and 2.84038. So essentially, I have 4 possible critical points: 0, 5, 0.66187, and 2.84038. My job then, because I have a calculator, is just to check in my calculator and see when f of t is the most negative at those options. So I'm going to give myself a little bit of room. So I need to find, so in my y1, I already have f of t. So I just need to find f of all those values. So I plug in f of 0 and get negative 2. I plug in f of this number, 0.66187, and get something in the neighborhood of negative 1.39760. I plug in f of 2.84038 and I get approximately negative 2.26963. And I plug in f of 5, and I get a negative 0.48027. The question was, what is the minimum value? When is this the most negative? And so my answer is that t is approximately 2.840 hours. Okay, notice that I didn't round my answer until the very end, right? I kept my answer with lots of decimal places until I was done. So the distance between the road and the edge of the water is decreasing the most rapidly at t equals 2.840 hours after the storm began. Cool. All right, so then my part D. Part D. After the storm, here's finally our rate in. After the storm, a machine pumped sand back onto the beach so that the distance between the road and the edge of the water was growing at a rate of g of p meters per day, where p is the number of days since pumping began. Write an equation involving an integral expression whose solution would give the number of days that sand must be pumped to restore the original distance between the road and the edge of the water. So, we already know how much sand was lost, right? So here's the idea, right? F of t was the rate that the sand went out, right? That's the rate that the sand disappeared, right? And g of p is apparently the rate that the sand is coming in, right? Sorry, there you go. All right, so the idea is we know that the amount of sand lost was the integral from 0 to 5 of f of t dt, right? And what we want is we want that to equal, right? We want however many days x, or you could pick a different letter, but I can't pick t, and so that's going to equal, and it doesn't matter where you put your negative here, right? This is a negative amount because it was lost. I want it to equal a positive amount that I'm gaining, so I put a minus in front. You put a minus in front here, you can put a minus here, that's fine. I want that to equal the integral from 0 to x of g of p dp. This 0 is day 0 when the pumping, or when the replacement sand starts. X is the number of days after. So this is how much I would gained in x days, right? So if we had the ability to solve this and they didn't actually give us a g of p, and you don't have to use these exact variables, right? Like, they called it g of PDP, so you might as well use g of PDP. You didn't have to pick x, you could have picked y. Like, you just can't really pick p, because p is already in this integrand. And you shouldn't pick t, because this t was measured in hours, and you're now talking about something in days. So you should just avoid mixing letters. But you could have picked any other letter that wasn't f, t, p, or g. Any of them would have been fine.